Hello, welcome back to our series, Behind the Scenes of Nautilus. I'm Commander Brad Boyd, Director Submarine Force Museum, and Officer in Charge, Historic Ship Nautilus. This episode, we're going into the control room, specifically ship's control and ballast control sections. Now, I'm going to do an overview of the entire area, which will include a radio and interior communications, but I'm not going to go into those spaces specifically until the following episode. If you have any questions, please let us know. With that, on with the tour. Alright, so last episode we left off here, and I said we would talk about the grand staircase here. So this is the grand staircase. It's so named by the ship's crew based off the size of it. It's the first time we've had a staircase this large. Prior to this, it's been like 3 or 4 steps to an area, but U.S. boats didn't really have that. Nautilus, you have to remember, was a Type 21 German U-boat design. So theirs involved having staircases like this, so Nautilus became the first submarine with a staircase. As we go down the grand staircase, we come into the control room. And as I said, we're going to talk about ship's control, which is this area here, and ballast control, the area back here, and a little bit about this navigation equipment that's back here. We'll talk about that this episode. And then next episode, as we turn around, we'll go over to this side of the control room, which is where radio and interior communications are. So radio communications on and off the ship. Interior communications is kind of the distribution of interior comms throughout. So, we'll talk about that next episode. As I said, back over here. So, ship's control would have had the 3 watchstanders you see here. Helm on the far side, stern planes in the middle, bow planes is closest to you. You'd have a supervisor, standing watch right here, called the diving officer of the watch. And you'd have a chief of the watch, the one standing back there, manning the control panel. So, it'd be a layout kind of like this. Although they wouldn't all be huddled around here. That was done mostly for the photograph, where you see bow planes, stern planes, helm, chief of the watch, and diving officer of the watch. So they're probably getting ready to submerge, based off the fact that the bow planes isn't doing very much right now, and we don't use bow planes on the surface, but he's stationed. So it's probably there as they get ready to transition from surface to submerged operations. That's my guess for how this picture's being taken right here. So, but over here, so as I said, you have the helm. So the helmsman controls left-right. So he would turn that steering wheel left and right to turn the rudder. So that's the plane in the back of the ship that goes up and down. So it's the vertical plane back, and that controls left-right of the ship. Then you have the stern planes right here. So he would push and pull on that yoke there. And that would cause the horizontal planes in the back of the ship to turn, to pivot like this, which then changes the angle of the ship up or down. And then you would have the bow planes who would throw those levers there, which would change the bow planes at the forward end of the ship, which are folded up while surfaced and folded down when submerged. And those would be used to help control depth. So stern planes controls the angle of the ship. Bow planes, really, its primary job is to help control depth. And then works that in conjunction with the chief of the watch, who brings ballast water on and off the ship in order to trim the boat at a neutral depth, but he helps change that depth. And will be used a lot at periscope depth as well, as you fight suction forces to pull you back up, as well as waves that push you down. So the bow planes and the stern planes work together a lot to maintain ship's depth, especially at periscope depth. So, all right. So you may notice these handles on the back of each of the chairs. That's the emergency control. So you have emergency hydraulics. So if the normal hydraulics, the steering and diving hydraulics, failed, you'd be able to shift to an alternate source of hydraulics for remote operation of the planes from here, so that the control team can work together. If that should fail, then you also have the ability to man the planes locally, but that would require people being on phones with each other so that the people who have indication of what the ship's doing overall can communicate to the person actually operating. Not ideal, but you do have the ability to take local control. On a I believe the 637 class is the one that changed. We combined the helm and the bow planes, or fairwater planes. If the extra set of planes are forward to the end of the ship, it's in the bow. If it's in the top of the sail, it's the fairwater planes. Just different locations, different term. But those 2 stations were combined, so we turned for left, right, and push for rise, dive, and stern planes was still an individual watch. So instead of 3 people, we'd have 2. And then Virginia class, we actually took those 2 people and combined them with the chief of the watch and the diving officer of the watch and called them pilot, co-pilot. And it looks very much like a cockpit. So that's Virginia class. So we went from 5 with Nautilus to 4 with the 637 class, all the way through the Seawolf class, and then 2 with Virginia class. So, okay, now as we look at all these individual spots, so you have compass is right there, so what heading the ship is on. This tells him what rudder angle he's at, so how far has he actually moved his rudder. The helm will control ordering the bell, so the officer deck says all ahead full. He would shift his telegraph, indoor telegraph, to full, which allows maneuvering to know when maneuvering answers. So as you let me move the wire out of the way. Maneuvering answers, so you see two arrows. One goes to where the helm orders, one goes to where maneuvering acknowledges that they acknowledge the order or they're answering the bell. Same here, so they all have ability to change. So he would ring up 2/3 standard full with that knob there, and then that would indicate what's happened and what maneuvering has acknowledged. Over here, so you see this is the angle of the stern planes or angle of the bow planes. Then you have angle on the ship, so a clinometer. So you have the fine one on the left, so within 5 degrees rise dive, and on the right it's the more gross adjust, so in increments of 10 degrees, and then angle on the control panels. Now something else you may not know. So right here, if you can see here, this is a selector to basically determine how sensitive the control surface is. So if you want to have adjust the stroke length, so therefore you would have how far that moving that control surface, moving the control for the control surface would affect the control surface. You would adjust this, so that way if you are going at high-speed operations, you don't want to have a full throw on the bow plane or the stern planes. You want it to be adjusted so that it takes a longer time to operate. That way, if you adjust this, instead of pushing full dive and you get a full deflection of upwards of 20 to 30 degrees of dive angle on the stern planes, you might get 5 to 10. And at high speeds, that increased angle could cause you to quickly almost lawn dart into the bottom or porpoise up and broach the surface if you're not careful. So that helps you do a more controlled approach as the helm or the stern planes, or the helm with the rudder order, same thing, or the bow planes, same thing. They all have that ability to limit it so that they don't throw the control surface as a normal response, as what they would think of, but at high speed cause a problem. So then over here you have some indications. So that's snorkel control power, panel. Indicates whether they got power of certain aspects, is it taking water in, is it up, all those types of things. And then power selection for your steering and your hydraulic controls for all these surfaces. So that's over here. Then as we come over here, and I apologize, you're probably going to get a little bit of glare, do my best to limit. So here you have your mast indications and, your hull openings. So you have engine room hatch, induction ventilation, main induction, snorkel exhaust, bridge hatch, all the various hatches. And then you have the vents below it. So do you have a flood vent on? So that's putting the water into your negative flood tank, your safety vent, same thing. All your ballast tanks, and then your safety tanks over there. And so a straight board, if you ever hear that term in a movie, that refers to the fact that it'd be a red open circle. Red circle means that it's open. A green line means that it's shut. So a straight board, you would have all shut indications or all lines straight across. So that'd be a straight board indication. Then you have the ballast tank operators. So ballast tanks on board Nautilus are a little bit different on a more modern boat, because Nautilus has a diesel boat hull design, which is, as I said in a previous episode, is basically a surface ship design, because that's where they spent the majority of the surface. Nautilus changed that, and we changed our designs to the albacore, and we'll talk about all that type of stuff in another episode, probably another video series down the road. But the ballast tanks were all around the sides, whereas a modern boat, the tanks are forward and aft of the ship. So 3 forward, 2 aft on like a Los Angeles class, whereas Nautilus had 5 just surrounding the ship. So tanks A and B, port and starboard, and tanks 1 through 5 all the way through. And these are the levers that would operate those valves. Then over here, high pressure air is essential for a submarine. So they would have 3,000 pounds of air available. And that would go to various parts of the ship. So you get high pressure air, service air, switch tanks on service to run various aspects of the ship. And then you would send air, cross connect air to basically equalize tanks and bring pressure up of one that's been utilized heavily, or charge up tanks as you use a high pressure air compressor. And then you could send them to like torpedo room, bow buoyancy tanks, the like, and that'll all be done from this station here. And then we'll step into here real fast before we continue the discussion. So over here, main ballast tank blow manifold, so you have the ability to blow your tanks dry in the event of emergency, or as just part of the surfacing procedure as you get closer. And so you align high pressure air to your ballast tank, blowing the seawater out, putting the air in, causing the ship to be lighter, and therefore surfacing. So you may notice that not all of these valves have a operator on them. That's because the operators are like this. You can take them off, and it's just a hole that lines up. But this way you don't have to have an operator for every single one. You can just have one sitting there and it'll be stowed in something like that, so that you have the ability to minimize the amount of space that each of the operator takes up. You don't have to have them all there. So this is the chief of the watch station. So here's chief of the watch. And his job is to maintain the ballast of the ship. Basically, he's kind of overviewing the entire safety of the ship's health of the ship, with the exception of the engine room. So he's looking at the sea pressures. These pressures, you can see things like sea pressure right here, which, by the way, there's a straight linear relationship between the depth that the ship is at and the sea pressure that it reads. So the ratio is 0.444 pounds per square inch for every foot in depth. So at 1 foot, it would be 0.444 pounds per square inch. At 10 feet, 4.44. At 100 feet, 44.4 pounds per square inch. And for example, like at 500 feet, it would be 222 pounds per square inch. So there's a direct relationship between sea pressure and depth. So if you ever think that your depth gauge is wrong, you would just take a look at your sea pressure, do a quick calculation, and let you know whether or not it's tracking accurately. But you also need to know sea pressure as well as your tank pressures before you go and place a tank in line with sea. You want to make sure the pressure that it's at is either above or below the sea pressure, so that you either ingest or discharge the amount of water that you want to move to the sea. So that you would bring water in from the sea to make the ship heavier out of the aft trim tank, the forward trim tank, the auxiliary ballast tanks, whichever one it is, to adjust your trim or your list. So list would be leaning left or right, trim would be up or down, so you don't have an angle on the ship. And then you would need to know your sea pressure for that. You would move water with a trim pump. And then usually you can, and I'm pretty sure you could do it in Nautilus case, although I don't have a drawing that proves it, but you could put the trim pump or the drain pump in line in the same system, and you can use one or the other to do the exact same function. But take a trim pump and you move water into or out of a tank, and you measure it in thousands of pounds, because on the ship I don't really care how many gallons of water I've got for trim purposes. I care about how many pounds of water I have. I care about gallons of water for fresh water, if I'm going to drink it or use it for cooling of ship's equipment, or if I'm going to use it for cooking or what have you. But in terms of weight for a trim tank or a ballast tank, I care about the weight of the water. So we put it in thousands of pounds instead of having to do the conversion of 8 pounds per gallon of water. But they would move the water around via the trim pump, and they would measure how much water they've moved by this gauge right here, and that would tell them and then they would also determine what the weight in the tank was based off the pressure sensors they have in the tank. And between the two of them, they could verify that they're getting the flow that they're expecting to, that the tank is reading what it's supposed to based off what they had move out, and they adjust the trim of the ship that way, and the list. Chief of the Watch also has the ability to adjust or raise or lower the ship's antennas, so not the periscope, but the communication mast. So VLF, loop, so very low frequency loop, BRA 9, BRA 19. So those are two different types of communication masts. ECM, direction finder, so that'd be probably the ESM mast. And then you have BIRD 6, BRD 6, another communications mast. And then you have UHF, IFF, so that would be your identification friend or foe. At one point, submarines would broadcast that all the time when they're coming into port or not, depending on your radio conditions. So that way you don't get mistaken for a potentially enemy ship. So you would broadcast your own frequency code to say, hey, I'm a U.S. submarine, or I'm a U.S. ship, or what have you. But anyway, so those are that's the operating operations up there. That's what these levers are right here. And then the mast indication in here. If it's all the way up, top light will be lit, top row will be lit. If it's all the way down, the bottom one will be lit. And if it's in between, neither will be lit, and it lets you know that it either is in motion travel or it failed to fully raise or failed to fully house. And that would be your indications here. You also have the Mark 19 Mod 3A Gyrocompass control panel, which goes to the Mark 19 Mod 3A Gyrocompass. So, the control panel, as you see right here, was used to determine ship's heading. And you could also look at the performance of the gyroscope, and you'd be able to measure what the gyroscope thinks is going on in the world, and that would let you be able to evaluate the function of the gyroscope, because they can fail. So this would let you take a look through that. Also, if you need to do any calibration or grooming of your gyroscope, you'll be able to do that from this panel here. You also have a Mark 23 Mod 0 auxiliary compass. So, and there's actually a control panel for that. Exterior to this, we'll cover that in the next episode. You have a fedometer. So we talked about fedometer and its functions last episode. We have one of the fedometers is down here. And it'll let you adjust where you think. So 100 feet or 100 fathoms, which 1 fathom is 6 feet. So 100 feet, 600 feet. So that's the same thing there. 600 fathoms would be 3,600 feet, and 6,000 fathoms would be 36,000 feet. So what you do is you put down what you expect the depth to be, and that adjusts the signal that you send out. So if you're shallower water, you need less of a signal. If you're in deeper water, you need more of a signal, because that's to go further to go down and come back. And so you would adjust the power that you have your fedometer set to, so that you don't just send noise in the water you don't need to. Transmitter gain, all those types of things. So that's what this was one of the fedometers for the ship. You have a control panel over here. It's going to be the ship's alarm panel and control. So you have the collision, the diving, the general alarm, and the propulsion plant casualty alarm. So the control room kind of functions as the nerve center for communications for the ship. Reports go into and out of here. Emergency communications, the officer of the deck is going to hear the officer of the deck maybe contacting directly with ESM or with sonar or with maneuvering, but general reports are going to come through the chief of the watch for your daily housekeeping type of stuff. And in the event of a casualty, control functions as damage control central, at least until the damage control central can be manned. Nowadays, that's out of the commanding officer's stateroom, just so they can have access to communication circuits and be out of the way of any response to a casualty. But that would come through control. And then also back here, so we talked about the compass. We're going to go back over here to the switchboard. So this switchboard is just an example of a distribution system on board. So power comes from the main bus, goes through these switchboards, and these switchboards then distribute that power out to individual panels or pieces of equipment if it's big enough pieces of equipment. For example, you have panels F2, 3, 6, and 7, so forward 2, 3, 6, and 7. So then you have equipment powered from that panel. So if you ever have a short in a piece of equipment, you would go to the panel. If you can't get to the panel, then you go to the main distribution points of these switchboards, and then you isolate those panels so that you quickly isolate power to that equipment. So if you ever have a short or a fire in a piece of electrical equipment, you would cut it off as low down as you can in the totem pole to minimize the effect of other equipment. But if you can't get to it, you come back further and further upstream to the point that you can isolate that. Because if you have an electrical fire in something, the fastest way to contain that fire and put it out is to secure power and stop feeding the fire. And you would eliminate the class Charlie, which a Charlie fire is an electrical fire. Alpha is a wood burning ash type fire, so anything that rubber burning, wood burning, paper burning, anything like that. Cabling burning is a alpha fire. The electricity that feeds that is a Charlie fire. And then Bravo is an oil fire, and Delta is a self-oxidizing fire. So if something produces its own oxygen, then you can't deprive it of it to put it out. That's a class Delta fire. Pyrotechnic would be a prime example of that. Flares, for example. But anyway, so back to the switchboard. And then you have the main power for the switchboard itself right there to kill all power to the switchboard. So, but that's just one version of a switchboard that's around here. All right, that does it for this episode. So next episode, we'll be going on to radio, and for lack of a better term, we'll call it the interior communication space. It's not really its name, but there's really not a name for it. Talk about that next episode. Thanks for coming along. Hope you enjoyed the tour, and we hope to see you soon.